So today we'll be investigating how the current through a device changes based on the potential difference we supply across the device. We're going to be looking at this for three different components. We're going to look at it for a resistor, we're going to look at it for a filament bulb, and we're going to look at it for a diode. So the whole purpose of this is to draw, to get some data so that we can plot some current potential difference graphs to see how the current changes based on the potential difference we supply across the device. So the circuit diagram is right there. You can see it's just an ammeter and a resistor with a voltmeter across the component. We've got the table, we've got potential difference one column, and we've got current in the other. So first, before we start, we'll just recap what potential difference is, we'll just recap what current is. So remember, potential difference is just the amount of energy that we're going to supply the electrons around the circuit with. If you give them more energy, in other words, if you push them harder around the circuit, they will want to flow faster. Yeah. And the only thing that's going to stop them from flowing faster, or so on, is going to be the resistance in the circuit. Okay, so if you see the setup that I'm going to do then, so I'm just going to set up the circuit just like in the circuit diagram. I'm going to start by connecting the ammeter. I'm just going to use multimeters here. So that first multimeter I connected will be our ammeter. There's the resistor. I'm just going to put that in as well, and then across it I will be putting the voltmeter. Okay, so remember, voltmeters have to go in parallel. Why do they have to go in parallel? Well, they don't conduct electricity, and we measure the potential difference across things. Okay, so there's the voltmeter, ammeter. Okay, I'm going to turn on the multimeters, and I'm going to turn on the supply, and I'm going to just test everything out, make sure everything's working. I'll just flick the ammeter around the other way just to get rid of that negative sign. It doesn't really matter that there's a negative sign, but it just annoys me, so I just swap it around. Okay, so I'm just going to collect readings real quick. So what I'm doing then is just changing the potential difference. I'm increasing it by 1 volt each time, and I'm going to measure the current every time as well. So I will just do that I'm just speeding it up really quickly here because it's really simple. I'm literally just changing the potential difference and measuring the current. Okay, and I just put it up by 1 each time. It doesn't take me very long, and it takes even less time if you speed up the video. So there's the results there. Now the next step for me is to do the exact same thing, except this time I'm going to be doing it with a filament bulb. And you might have seen with the results before, you might have seen a pattern. Do you think the same pattern will appear with a filament bulb? So the pattern we saw with the resistor, it was going up by the current was going up by roughly the same amount each time. So roughly the same amount each time. You'll see that I mean in the follow-up video when I plot a really quick graph of that. Do you think the same thing's going to happen with a filament bulb? With a filament bulb, it's going to behave very similarly to a resistor, except the filament is actually going to warm up. Resistors are designed to not, where their resistance shouldn't change too much with temperature. However, a filament bulb isn't designed in the same way. It's not designed to keep a constant resistance. So how do you think this is going to affect our results? Well, let's find out. I'm just going to dial in 1 volt. Of course, both cases, 0 volts will produce 0 current. You don't push the electrons at all. They're not going to move. So you're going to get 0 current. So when I dial in 1 volt, I get a current reading. I'm just going to work my way through to, I think I work up to about 7 volts again. It's important to mention as well, actually, if I did change the direction of the potential difference and reverse the flow of the current, then they would behave in exactly the same way. Okay, at least the resistor will, and the filament bulb will. So you can see as I'm up in the voltage, the bulb's brightness goes up as well. So we've got a bright bulb at the minute. I would have done more, but I ran out of table, unfortunately. The table on my table. Right, so I'm just going to unplug the bulb, and I'm going to plug in a diode. But notice as well, I'm also actually going to put the resistor back in. Now you'll see why we do that when we look at the results. But essentially, it's to protect the diode, because what happens with a diode, you get to a certain voltage and the current, the resistance goes right down. yeah, which causes a huge spike in current. If I didn't have a resistor in series with it, then it would possibly break the diode. It would cause a lot of current. A lot of current means a lot of heat, so it'll warm up very quickly. It'll be almost like a short circuit, where I could potentially damage not just my diode, but also my multimeter. I just accidentally drew the circuit diagram wrong. Now, there is a problem with this circuit diagram right now. If you know about what a diode is, okay, I'll just pause it. If you know about what a diode is, then you might see something wrong with this circuit here. So my circuit diagram is drawn incorrectly. I didn't pick this up whilst I was filming. See if you can think of what it is. So have a look at the battery or the cell. It's actually the current is going the wrong way through the diode. Now remember, a diode does not allow current to flow through it under reverse bias. That means it cannot flow backwards through it. So this is why the diagram's wrong, but we can just pretend it's the other way around for now. So here I do the same thing again. I'm just testing it to make sure I've got the diode around the right way, make sure I actually get some current out of it, and I do. So I can go ahead and take some readings. Now this time the readings I'm not going to go up to 10 volts because obviously the potential difference of the diode changes. The resistance of the diode changes to practically nothing as I get higher up through voltages. So I'm not actually able to make it to 10 volts because all of the potential difference is being taken up by the resistor, and it causes quite a big current to flow. You'll see what I mean in a minute. So currently it's not going up too much. The potential difference is going up by a very small amount. The voltage is going up by a very small amount, but that's not going to continue. Okay, the voltage will continue to go up by a very small amount as I increase the supply, but have a look at what happens to the current in a moment. So what I do try as well at the end is I try and get the voltage up as high as I can, very nervously turning up the voltage as high as I can to see what happens, and I don't keep it on for very long because I don't want to break the diode. And you know, if Mr. Watling's watching this video, I don't want to break his diodes. So notice, look, the current is actually going up quite a lot compared to the voltage right now. So I've not even really gone up by, you know, maybe 0.2, something like that, volts. So the current has gone up by quite a lot, 0.1 volts even. Yeah. So this is me just ramping it up as high as I can get the power supply, and I get it to about 1 volt across the diode, and I get about 6.5 ohms out of it, 6.5 amps out of it, sorry. So, you know, if I left that to run for a little bit, then undoubtedly I would break something. Possibly the thermal cutout on the supply would go first, but I don't want to risk that. Right, so there's my results. So I just turn everything off just to make sure it's all safe. And I'll see you in the follow-up video where I'll draw a few current potential difference graphs for you.